This video is just an update on on what importance what are important to the lecturer that he feel must be so-called reminded. Alright, so therefore in this video we'll discuss on the things that the lecturer has reminded us to take note of, and let's go. The first one he wants to mention is the nickel titanium alloy, and please take note that this nickel titanium alloy is a super elastic and it is also a shape memory alloy. If you were to head to over here, alright, super elastic is this, maybe I should, you give me a while. Super elastic alloy is this one, so shape memory alloy is this one. Alright, super elastic by itself is when you input a certain loading, alright, you will start to yield. Alright, this is a stress strain curve. Alright, so you start to deform and up to a point when you release, alright, it will load back to its original thing. Alright, so in other words, it does not cause any strain at all. Alright, it's just elastic, just like a rubber band. Alright, and as well as when if happen that if it's kind of deformed, if happen that it will deform, alright, at this position over here, if you heat it up, alright, it can actually return back to its original shape also. Okay, so you will not actually cause a permanent deformations. You can either heat it up, or when you unload, you elastically so-called go back to its original length or things like that. So do take note of super elastic and shape memory alloy, that your nickel titanium alloy has it. Okay, your nickel titanium alloy, and is used for braces. And you may want to discuss on the bonding issue, or this diagram over here. Alright, he actually said that the bonding change with temperature. Alright, if you remember, alright, it exists as a martensitic structure, alright, which at its normal temperature. Maybe I should use, you give me a while. So I should remove this thing first. Alright, but in the exams, if you happen that they need you to draw this, please include these two things. Okay, so I'll just place it beside here in case that you forgot. So normally we'll start off from this. It's a Martin, maybe I should zoom in a little also. So we start off with a martensite twinned low temperature. Alright, so it's in this, arranged in this manner. Alright, and martensite itself is a high strength material. Alright, high strength meaning very hard. Alright, however, it has low yield strength, meaning it's easily deformed. Okay, don't confuse high strength and low yield strength. Alright, strength is strength, yield strength is yield strength. Don't confuse between them. Okay, but nonetheless, this is the thing. At low temperature is easily deformed. So when you deform, you'll become like this. Alright, the martensite is being deformed, and therefore when you use a certain high temperature, the bonding changes. Alright, and this heating give recovery. Alright, changing the whole structure back into a neatly arranged type. Alright, it's an austenite high temperature. Alright, austenite is just a high temperature system. I'll not go into details, I assume you know. Alright, and after that, when you cool it faster, or when you cool it very fast, alright, you'll eventually become martensite. If you cool it slowly, you'll become pearlite or ferrite in a certain sense. Anyway, yeah. So the different bondings, you should take note of it. Alright, the drawings all over here, you should take note of it. And if you want to know more, suggest 10.6, 10.7, 10.8 of the playlist. Alright, where it talks about nickel titanium alloy and its applications. It's a full scale thing. If you want to know more and more, you can go from v10.1 starting from it. Alright, talking about high strength low alloy steel. Alright, where it's part of an advanced metal, if you want to know the full general understanding. But nonetheless, these 8 videos are the one that is relatively useful. Okay, so the next one is this page 21. Alright, from your metals lecture note. Alright, it's the same after the next page, a few pages later. Okay, 2 pages later, you'll arrive to this thing. Okay, where it talks about also nickel titanium shape memory alloy, where it's being used as a spring. Alright, so this spring, when heated, it will expand. Alright, it will grow taller, as you can see. Maybe I should, you give me a while. So when heated up, it will expand. When cool, it will it will contracts. Alright, so this can act as a mechanism. Alright, so one thing that I've learned through other stuff during my FIP is you may actually have a certain uh, heat transfer type of material. Alright, maybe wires or what. Alright, so when you transfer heat through this thing over here, you also transfer heat to the nickel titanium alloy, where over here when it receive heat, alright, it will actually so-called increase its height or deflect. Okay, sorry, I should say something. I think if let's say, alright, if there is no heat, give me a while. This thing over here, it's normally when you have a heat, you will expand. When it is cold, you will contract. Oh yeah, okay. So therefore, when hot is expanded, when cold it's being, yeah, so you have a certain wiring over here to transfer the heat, maybe some resistance. Alright, so this resistance will cause heat, which will expand if you need the spring to expand. If you want it to be so-called contracts, you can release or you can off the power so that there will be no heat transfer from here, and therefore the spring will slowly deflect into its original position. Okay, so in between there is a deflection over here. Okay, and the equations, everything over here I will not discuss in this video because I will highly recommend you to watch 10.7. Alright, it's a deeper approach in explaining sheet memory alloy. And at this particular point, about 20 minutes, damp out anything. So I don't know how exactly. So it's starting about from 18 minutes onwards. Alright, 18 minutes. Expensive, I think. So you'll start to talk about that. Often going. Yeah, so you'll talk about this in a video. So I'll not go into details on it to keep things short and summarized. I also assume that you have already know all this because this is the 11th week already. The video was in the 10th week, so you should watch that video before coming back here. So yeah, but what I want to highlight over here after reading a bit is that these two equations, alright, they are used to find the force acting on the spring. Alright, it's talking about the force needed. So these two equations are to calculate the force. Okay, it's happened that they ask you to calculate a force, then you will use this type of equation that comes about all along. Okay? No, I am talking rubbish, sorry. This thing over here, alright, includes the P already, over here. So if you want to find the force acting on the thing, you will just need to rearrange. So in order to find, normally we will need to find the P value. Okay, but nonetheless, this equation you must remember. Alright, it's not given to you. If, yeah, most probably you need to remember. Okay, so if happen that you need to remember, P, if you rearrange, you have this equation. So this equation is after you rearrange, you bring everything, all these things to this side. Alright, so you will find P. Alright, so this is something that you need to be aware of how to manipulate your equations to the one that you want. Okay, hopefully this kind of clear up your stuff over here. So over here he wants us to, so this is the next one. Okay, if you were to go to tribology lecture, page 19, this page over here, he says that the location of the maximum shear stress is half of the indentation radius A. I assume that you know A is what already. If you don't know what the hell is this, you can watch these few videos on Hertzian stresses, Brinell harness testing. Alright, and as well as all these tutorial questions. Okay, where it will go into in-depth. Alright, especially this field 9.3, 9.4. You just search for this videos, or eventually, and the keyword is Hertzian stresses. Alright, or Archer's equation. Okay, where is it? Never mind. Or you can search for the keywords like impression radius. Alright, impression radius A. Okay, so I'll not go into details of what the meaning it is. I assume that you already know. So he just want to let you know that the location of the maximum shear stress is 0.5A. Alright, and that's something that you should take note of. Okay, it's the maximum or around, because I will assume that it's 0.6 plus minus 0.1. Alright, but he says it's 0.5, so let's just take it as 0.5 then. Just take note of the like surface contact, this type of equations, or later on we'll also discuss this problems again. Okay, I think this may be the one that is coming out in the exams, I don't know, but just take note of there's another term called reciprocal radius. Alright, because it's reciprocal, the one divided by something is considered reciprocal, I think. I forgot already, but yeah. So take note of that, but it's called the mean contact radius or the contact radius. Okay, so it can also be called reciprocal radius. So it happened that in the exams they call you to find reciprocal radius, at least you know what the hell is it. Okay, so over here the next one is at page 25. Okay, I think, yeah, 25. And there is this oxide layer over here. Alright, and this is what it says is that after you have a certain let me see, the oxide layer over here exists in most metal. Alright, this is an oxide layer to protect the layer, I think. So deposition of soft metal on hard substrate lower the shear stress. Yeah, so what I mean is that the rider, the rider is always the hard material. Okay, and it happened that because the oxide layer over here, this is softer than the metal itself. Alright, I repeat again, this oxide layer is softer than the metal itself. So the softer oxide layer will actually so-called stick onto the rider. Okay, and this will actually reduce the shear stress. That's what I would believe is the meaning of that. Alright, so because of the term he says is sacrifice oxide layer. Alright, softer material will chip off. Alright, the chip off. So the softer material will being stick onto the, I don't know where's the picture, forgot. Yeah, over here. So a fragment of the softer material will also will kind of stick onto the hard material and it will move off. Okay, so this is something that you should take note of, and therefore it comes into the Archer wear law, where you should take note of the volume being removed by the wear. Or these are the equations I'll not go through, adhesive wear and etc. And these wear equations can be so-called reference from here onwards. Surface wear testing, I don't know where the hell. Yeah, but these are the fields that you can take note of it. Alright, you can watch the videos to gain more understanding from there, because I already forgot what are they already. And these are the things that you should know. And one more thing that I want to highlight is you need to know how to draw this type of figure. Alright, wear testing. Alright, so this type of figure is also discussed in that video, so you can watch it. But you just need to know that this circular rotating disc is really rotating. Alright, so the rotating disc is a hard material, while the test material, the test specimen is a soft one. So when you test using the soft one, you'll get to know how much wear and tear will it be. So this will come back to the amount of volume being wear off, or the wear debris, which is also the same equation that I said just now earlier. Same thing. Okay, so be careful of all this little stuff. So in that 3 videos it will talk about it. So yeah, because that will be clearer. That time I took quite an effort to do that. Now I forgot much of the things over here, so I need to recap myself also. So nonetheless, you should take note of how to draw this in the exams, because it might be a potential question to ask you to draw, and you need to label all this stuff. I'll not explain all of them, but you need to know this awareness of it. Okay, and last but not least, I also want you to take note of this 3 videos. Tribology tutorial question 1A. Please watch that videos, because he went through again on that. Where we'll talk about how to calculate the amount of Brinell hardness, or the amount of hardness depth that you need, things like that. So I'll not go into details on here in this video, but I will just want you to watch these 3 videos in order to understand. Especially question 1B and 1C, there is some values discrepancies here and there, so I want you to take note of it before you go into there, in case you may feel a bit confused. But it has the concept that is generally acceptable. So yeah, and I'll update again in the next week. Alright, the revision week. So yeah, and in the next video I'll talk about another question doesn't appear in anywhere, but I just want to highlight over here. So see you in the next video for tutorial question. Yeah, bye.